Hello everyone. So modern languages like ChatGPT, Claude, Anthropic, and Gemini do not understand the languages the way we humans do. They do not think, reason, or know facts. Instead, they operate entirely on mathematical patterns learned from massive amounts of the text. When we type a message into something like ChatGPT, a long pipelines of numerical operations begins. Our words are converted into numbers, processed through a neural network, and then transformed into probabilities. The model then generates a response, one piece each at a time. To understand how this really works, we first must learn several foundational concepts like tokens, tokenization, embedding, logic, softmax, fine-tuning, inference, hallucination, FLOPs, etc. Okay. So, what is a token? A token is the smallest unit of text that a language model can process. Language models do not read sentences or even words directly. Instead, they read tokens, which can be whole words, part of words, punctuation mark, or symbols. For example, if we look at this word unbelievable, right? So this word is broken into un, believe, able, and punctuation mark. Each of these pieces is a token. Internally, every token is a map to a number, and the model never actually sees the actual text. It only sees the sequences of number. For example, un might become 1024, believe might become 9876, able might become 657, and punctuation mark might become 12, right? So instead of model or seeing the word unbelievable, it just receives numbers, right? Now, if we take the example of like a real life situation, think of tokens like Lego bricks, right? Language is built from small blocks, and some blocks are large, entire words, while others are very small, like fragments or punctuations. The model builds meanings using these blocks. Now, let's talk about tokenization. So, tokenization is the process of converting raw text into tokens. The neural networks cannot process letters or words directly. They can only process numbers. Tokenization is the step that converts human language into those numerical forms. For example, if we take this sentence, I love AI and punctuation mark. This will be tokenized as I love AI and the punctuation mark, right? Each token is then converted into an integer ID. If we want to take a real world analogy, tokenization is the scanning of like products at a supermarket. The cashier does not care about the word milk, the scanner just reads a barcode number. Similarly, AI scans your sentence and converts it into token IDs. Now, why tokenization matters? Tokenization explains why small changes in wording can change AI responses. It also explains why longer prompts cost more in APIs and why every token requires computation. Now, let's talk about embeddings. So, an embedding is a numerical vector that represents the meaning of a word, sentence, or document. Each token is converted into a long list of numbers, often containing hundreds or thousands of values. These numbers represent semantic meaning. Words with similar meanings are placed close together in this high dimensional space. For example, if we see the king is placed close to the queen, right? A dog will be placed close to a puppy, or sad is close to depressed. But a banana is kept really far from the king and the queen. To give you a real life example, let's take if we write, I feel lonely today on ChatGPT. ChatGPT converts this into embeddings and finds nearby emotional concepts such as sadness, tiredness, or isolation. This is the reason why it responds with empathy, right? If we take the uses for like Claude or Anthropic, Claude uses embeddings heavily for document understanding. So when we upload a PDF, Claude split it into chunks, create embeddings for each chunk, and searches through them using vector similarity. Now, to give you a real life analogy, embeddings are like GPS coordinates for meaning. Just as cities exist on a map, word exists in a semantic space, right? Now, let's talk about logics. So, logics are raw numerical scores that are produced by the model when predicting the next token. So, when we type I love, right, the model might generate scores like it generates AI as 5, pizza as 4.2, or 3.1 for you. So these numbers are not probabilities, but they are simply relative preferences. To take a real life analogy, logics are like votes. Higher numbers means the stronger preference, but they do not yet tell you the percentages. Okay. Next, we have softmax, right? So softmax converts logics into probabilities. After softmax, the previous scores might become like AI is 59%, pizza is 30%, and you is 11% from the above sentence, right? Now these values sum up to 100%. So the model either chooses the highest option or samples randomly based on these probabilities. This is the reason why ChatGPT sometimes gives you slightly different answers to the same question. Now, let's talk about fine tuning, right? I'm pretty sure you guys have heard of fine tuning a lot of times. So fine tuning is the process of training a pre-trained model further on a very specialized or specific data, right? Large models are first trained on general internet text, then they are fine-tuned on curated data sets to improve behavior. ChatGPT is fine-tuned on human conversations and feedback so that it becomes helpful and polite. Claude is fine-tuned using Anthropic's constitutional AI principles, which emphasizes safety and harmlessness, right? Medical models are fine-tuned on clinical documents, so they learn medical language. Now, to give you a real-life analogy, per training is a general education. Fine-tuning is professional training, right? Now, let's go with something called inference, right? Now, inference is the process of generating answers after the training is complete. Every time we use ChatGPT, we are performing inference. So during inference, a text is tokenized, the tokens are converted to embeddings, the transformer network processes them, then the logics are produced, softmax converts those logics into probabilities, the one token is then chosen, and the process repeats itself. Each word we see is generated one token at a time, right? Now, let's talk about hallucinations, right? Hallucinations occur when a model produces incorrect information confidently. This happens because language models predict likely text and not like the factual truth. If we ask a fictional event, the model may invent details because it is optimized to continue the patterns and not verify the facts, right? For example, if I ask who won the Olympics in 2035, now we are in 2026. So what will model do? It might fabricate an answer, right? Now, why hallucination occur or why hallucination exists? The model maximizes the probability of language and not the accuracy of reality. How companies reduce hallucinations? So there are modern systems, they use RAG or retrieval augmented generation, which pulls real documents from databases before answering. Again, for example, ChatGPT browsing and Claude citations work in this way. Now let's talk about FLOP, or floating point operation, or flops, right? So FLOPs stands for floating point operations, right? It is a measure of how much computation is required. Training GPT-4 requires approximately 10 to the power of 25 operation that involved thousands of GPUs running for like months. Even a single ChatGPT reply requires billions of operations. Although I don't really know, but yeah, it does. To take a real life analogy, FLOPs are like engine horsepower. More FLOPs means more intelligence, but also more electricity, heat, and cost. Now, let's go to part 2 of this. Here, I'll try to explain you all these concepts with maths. Now, this is a point where like a lot of people lose interest, but I think this is required. So if you guys can bear me, please proceed ahead. If not, I think yeah, these are like the basic concepts which you needed to understand. Now, let's get into the real stuff. So, first question is, what are LLMs, or large language models? So LLMs are AI models or neural network that understand and generate human language. For example, ChatGPT, Claude, Gemini, Llama. Think of them as super smart autocomplete systems. They predict the next word in a sentence based on all the previous words. The core idea is autoregressive language modeling. Now, what is autoregressive language modeling? This is basically the heart of how LLMs work. So, to give you a math foundation, suppose we have a sentence, like I have a cat, right? So, let's say if I say the cat sat on the mat, right? Now, in LLM models, the probability of this sequence. So, they take the probability of the cat sat on the mat and then split it. So first they'll take the probability of the times probability of cat slash the times the probability of sat and slash the cat, so on. So if we say it like, for more formally, for a sequence of tokens, words or subwords, it's like x1, x2, x3, so on till xn, right? This is called the chain rule of probability. Here, there is no approximation, it's exact. So autoregressive means predict the next token given on all the previous tokens, right? Now, in tokenization, tokenization is turning words into numbers. Computers don't understand words, so we convert those texts into numbers or tokens. Now, why can't we use the whole words? For example, the one major problem is typo problem. Instead of HELLO, hello, someone types to HELO, hello, or something else, we have these cool words. So now that's a very unknown word, right? Or if there are languages which exist without spaces. I don't know how many of you know Thai. I don't know Thai, but I know that it is a language without spaces, right? So that creates the problem. The third problem we face is long sequences. So character by character makes sequences too long, and that slows down the training. For this, we have something called BPE, or byte pair encoding. This is a very common tokenizer. So what is the process? It starts with each character as a token. Then it finds the most frequent pair of tokens and merge them into a new token. And it repeats until we have a desired vocabulary of size like someone from like 25,000 to 100,000 tokens, right? So if we have a sentence like low, lower, lowest, right? So step 1 will be divided into L, comma O, comma W. Okay. Then space L for, because now we are going to lower, right? So space L, comma O, comma W, comma E, comma R, comma space L for lowest, space L, comma O, comma W, comma E, comma S, comma T, right? Now this is how we splitted them into low, lower, lowest. Now step 2 is to merge, right? L plus O, which gives LO. Now if this is frequent, we merge LO plus W, which makes low, and now LOW is one token. If you don't understand this, don't worry, I'll make separate videos on this in future. But for now, what I want you to understand is how tokenization works, right? So the vocabulary size is equals to the number of unique tokens, right? This basically becomes the output size of the LLM. Now, let's go pre-tokenization. So before BPE or byte pair encoding, we often split by spaces or punctuation mark for efficiency. For example, if we take hello, comma world and punctuation mark, right? So hello, then it will be splitted by comma, then again comma, then word, then comma, and the punctuation mark. Now this is the process of pre-tokenization. Before we tokenize this, we split, right? Now, let's talk about the model architecture. So LLMs use transformer architecture. Now there are few points which I want you to understand. First is self-attention. Self-attention basically weighs importance of each word in the context. Now there's something called positional encoding, which adds order information, since transformer don't inherently know the word order, right? Then there is something called FFL, feed forward layers. Now these FFL process those information. So we input, then there is token ID, from that we have embedding layer, like each token gets a vector, then we have transformer blocks, then we have output layer, like output layer is basically logits for each token, then we have softmax, which is like probability. So if suppose a vocabulary size is of 50,000, then its output is a vector of 50,000 logits, and then we have softmax, then we have probabilities for each possible next token. Now there is something called training or the loss function. So we use cross entropy loss generally, which is basically the negative of log, right, of the likelihood. So for example, for a correct next token y, one hot vector and the model prediction of y bar probability, the loss will be equal to minus of summation of y log y bar, right? In this, y is like one hot, which is like one for correct token and zero elsewhere. So this simplifies loss is equals to minus log of y bar correct, right? Again, I'll try to give you these formulas either in terms of PPTs or like in my notebooks, so that you could go through these later, right? For now, I just want you to understand how LLMs really work. I'll teach you how to build one in another video. Now, perplexity measures how confused the model is. The lower is the better, of course, right? If it's higher, that means your model is really confused. Now the formula for this is exp of 1 by L summation minus log p of xt by x t is greater, right? So here L is like the sequence length. Of course, you'll not understand this math part. I'll again take a lecture on evaluation in which I'll explain you these maths completely again. But I just want you to understand for now what I'm saying and not focus on the maths part, right? So a perfect prediction means the perplexity is equals to 1. And random guessing from V tokens, that means perplexity is equals to V. Now, there's something called data collection and cleaning. So training data generally comes from the internet, right? And I think there are 250 billion web pages, right? So what happens is they extract text from HTML. They filter the undesirable content like NSFW or toxic, then they deduplicate it. That means remove the repeated text. Then there's something called quality filtering, where there is heuristic or model-based classifiers. Then comes domain balancing, which is basically like mix of Wikipedia, books, codes, etc. Data quality matters more than these architecture tweaks, right? Now, let us talk about the scaling laws, right? There's a surprising fact. Bigger the model and plus more data is equals to better performance. Okay. Of course, it's no biggie or no surprise, but a lot of people tend to miss on this. So bigger model plus more data is equals to better performance. Now compute optimal training or chinchilla. So for a given compute budget or balanced model of size n and training of tokens d, so optimal is equals to n times c to the power of 0.5, like it's directly proportional, right? Where c is like computation of FLOPs, right? Then there's something called rule of thumb. Again, I will not get into much of the details. I'll explain you what is rule of thumb and then I'll explain you it in the upcoming videos. So 20 tokens per parameter for training is optimal, right? For example, if we have 1B parameter model, then it trains on almost 20 billion tokens, right? Now, the pre-trained LLMs aren't yet helpful chatbots. So what we do alignment. There's something called supervised fine tuning or SFT. So we collect human written examples like the instructions or the good responses. And then we fine tune those LLMs on these examples using the same cross entropy laws. And then we teaches these model to follow these instructions. So there's something called RLHF or reinforcement learning from human feedback. And then we have the evaluation of these chatbot, right? So there's like human evaluation where there's like, what do you say, blind comparison. Then we have even LLMs as like judge. So we use ChatGPT 4 to compare, responses, etc., etc., right? In the upcoming videos, I'll explain you about like complete maths and code behind autoregressive likelihood, cross entropy loss, perplexity, scaling laws, chinchilla optimal, reward modeling, which is also known as Bradley-Terry, right? Etc. So for now, I have explained you token, which is basically a chunk of text, then tokenization, which is basically like converting text to tokens, then embeddings, which is basically like the vector representation of a token. Then I explained you logics, which is basically the raw model output before the softmax. Then softmax, it converts these logics into probabilities, right? Then we did fine tuning, which is like, further training a pre-trained model on a new data. Then we have inference, which is like using the trained model to generate the text. Then we have hallucination, which is like model generating false information confidently. And then FLOPs or floating point operations, which is like measure of the compute. Hope you enjoyed today's session. Thank you.